Hello everyone, Aaron here. Welcome back to Leetcode. Today we are doing the increasing triplet subsequence problem. Given an integer array nums, return true if there exists a triple of indices I, j, k, such that I, j, and k are in order, and the values in the array nums are also in order at those indices. Return false if no such set of indices exists. So here, obviously 1, 2, 3 works, 1, 3, 5 works, 2, 3, 4, anything works. Well, not anything, but almost anything. Here, nothing will work because everything down here is smaller than the things before it. So although the indices are always increasing by definition, the values there never do. And here, for this last one, we have lots of options. So they say 3, 4, 5 is valid, 0, 1, 2, 3, 4, 5, 0, 4, 6. They are increasing. But you could also do 1, 5, 6, for example, or 2, 5, 6, or yeah, there's options. So I actually think I did this one a long time ago when I was trying to learn a bit of APL. So I thought it might be fun to actually do it in APL. Now, unfortunately, APL is not one of the languages supported on Leetcode. So we're going to have to translate it back into, say, Python, and then go about making it faster as we need to, kind of thing, because the two languages have quite different profiles for how fast they are. But I want to do it in APL. So I've got the same problem again here, and I have my Emacs set up for writing APL. So let's start with, well, let's say we're doing this test case here. 1, 2, 3, 4, 5. In APL, we can do that with I5. Whoops, that jumped all over the place, but 1, 2, 3, 4, 5. We have those. So how is our function going to work? The way I think this should work is that basically we want to keep track of the smallest value we've seen behind us, the largest value we've seen in front of us, and then work out whether we're in between those. So here we're at position 3. The smallest value we've seen before us is 1. The largest value we'll see after us is 5, and 1, 3, 5 works. Whereas here, if we're at 3, the smallest value behind us is 4, and the largest value in front of us is 2. We cannot squeeze in that gap. There's no gap to squeeze into, basically. Here, if we were to do the 5, the smallest value before us is 1, and the largest value after us is 6. So we do squeeze in the gap. Whereas if we looked at the 0, the smallest value before us is 1, and the largest after us is 6, so we don't squeeze in the gap. So that's going to be my approach. What's the smallest before us, and what's the largest after us? So one way to do this in APL would be to do a scan of the minimum, in fact, no, that's the other way around, a minimum scan of the argument. What's the smallest thing we've seen at each point? Let's do this with the third example because it's a bit more exciting. 2, 1, 5, 0, 4, 6. The smallest we've seen is 2, the smallest we've seen is 1, the smallest we've seen is 1, the smallest we've seen is 0, 0, 0. So you can see here this is telling us at each index what's the smallest thing at or before it. We also need to keep track of the largest thing after it. Now, we could start similarly, and I think we will. This tells us the largest thing we've seen so far. The largest thing I've seen so far is 2, 2, 5, 5, 5, 6. And sure enough, that's what we see here. But I don't want the largest thing I have seen. I want the largest thing I will see. But of course, that's just walking backwards. So what we can do is we can reverse the input array. So here we see the 6's carry all the way back. But if we had, say, a 2 on the end of this, that 2 would be at the wrong end. So we need to reverse it again. The largest thing in front of us at any given point. Here, the largest thing in front of us is a 2, if we're at the end of this array. Let's get rid of that, just for testing purposes. So, using this incantation here, we have the... using this incantation here, we have the smallest thing before us, and down here we have the largest thing after us. So let us actually do both at the same time. How do I want? If I want to do, I want to do an enclose. I want to ravel that next to the enclose of. Let's do our. Oh, I had that right. I want to do a minimum scan of omega. So here we see the two pieces that we're after. There's 2, 1, 1, 0, 0, 0, and there's 6, 6, 6, 6, 6, 6, 6, 6. What we want to do is we want to find if the value we're actually looking at squeezes in the middle. Now, the value we're actually looking at here is omega. This guy, this guy, this guy. So does 2 fit between 2 and 6? Well, not perfectly, no. The 2 meets the 2. But does the 2 fit between a 1 and a 6? Yes, it... does the 2 fit between a 1 and a 6? Yeah, it does. So, no, not the 2. Does the 1 fit between a 1 and a 6? No, it doesn't. Does the 5 fit between a 1 and a 6? In fact, no, let me reorder these slightly. Let's get rid of these encloses. And then I want to do a reshape. I think this is going to be a 3 reshape. Oops, no, a 3. Shape of omega. Maybe I put that the wrong way around. Shape of omega. 3 reshape. Nope. Oh, I need to put parentheses around it. That's the problem. No, that's not the problem. What if I just do a 3-3 reshape? That works. Well, hang on. How many elements do I have? 1, 2, 3, 4, 5, 6. Let's just do a 3-6 reshape. Yeah. So these are my minimums. These are my values. These are my maximums. So now we're looking at the columns and seeing where the middle squeezes in. So no, no, yes, no, yes, no. So there are these 2 cases where it works. The 1, 5, 6 and the 0, 4, 6. In fact, we could do a 1, 4, 6 too, but 0 gives us an even wider gap. And that's all we need to work out. We don't need to work out what every gap is. We just need to work out if there is a gap. So now we have these 3 things. Rather than join them all together and print them out nicely, what I want to know is, where is it the case that omega is greater than the minimum and less than the maximum? Now, obviously, this is sort of Python-y notation, but we can't really do that. So what I need to do is I need to say, is it that one? And omega is less than. So where is omega greater than this, and where is omega less than this? And sure enough, it's those 2 columns we talked about. Now, this guy here is a little bit gross because we've got this extra pair of nested brackets here. So what I could do is actually just move my omega to the other side so we can get rid of 1 layer of brackets. Now, This tells me that there are two combinations at least where this will work. But I don't care. I just want to know that there is any case where this will work. Sure enough, there it is. Let's try the other test cases. So remember that iota 5 was one of our test cases. And sure enough, it comes back true. And also remember the reverse of iota 5 was one of our test cases. 5, 4, 3, 2, 1. This should be false. It is false. We don't need spaces in here. That was just to make things a little more readable. So what we've got here is triples is defined as, is it that key? Yeah. This. So I can now do triples of 2, 1, 5, 0, 4, 6 is true. And that is how you solve this problem in APL. Now, as I said, we can't actually put APL into Leetcode. So we're going to have to re-implement this idea in Python. So it won't be quite this short, but let's take it across. Just so I can reference what I'm doing. Now, back in Python. So what we want to do is mins is, well, basically it's going to be the min of nums up to I for I in range len nums. Maxes is going to be max nums up to, in fact, it's going to be everything after I plus 1 for I in range len nums. In fact, no. That is what I want. So let's just check I've got those right. Print mins maxes. Yeah, that's expected. Let's use this test case. Just to see if that matches what we were getting in APL. It does. Excellent. So now what I want to do is go, well, basically what I need is I need to do x, y, z. In fact, no, it's mins I, nums I, maxes I for I in range len nums. Print triples. This is a lot clunkier than it was in APL doing this kind of development. Yeah, so we got the 226, the 116, the 156, and the 046. Remember, those are our two cases where we were arguing that this works. So we can actually do this here and say, well, actually, let's just do this mid comparison. Python actually lets us do this. And we see there are two cases where it's true. So what we actually want to have is any, which is a built-in in Python. Whoa. In fact, we don't need to print it out. We can just return it. That's horribly slow. Only took 73 milliseconds, but it did not take 73 milliseconds to render. So this works It's not very fast. The APL is doing some tricks to make it a bit quicker. In particular, this is horrible. So let's fix that. Mins is equal to the empty list. Min so far is equal to num0. In fact, this is going to be nums0 for I in range len nums. What we want to do is mins.append min. In fact, hang on. Min so far. Far is the min of min so far and nums I plus 1. Mins.append. I need a -1 in here because I'm doing a +1 there. Min so far. In fact, I can because I can avoid some of this complexity by just comparing it with itself once and not storing it in there. Same for maxes. Maxes is the empty list. Max so far is nums -1. For I in range len nums -1, -1, -1. This is iterating in reverse. Max so far is the max of nums I, and max so far. Maxes.append max so far. And again, this is the wrong way around. So we're going to do maxes.reverse. And then this check should now pass. Let's test it, see if we've broken anything in the meantime. Fantastic, we've not broken anything in the meantime. I'm a little worried this is a wee bit slow. So it's big O notation. This is order n. This is order n. This is order n. This is order n. So overall, it's order n. It's a 4n, but it's order n. So that's correct for that. Now our space complexity is a bit large. Our space complexity is effectively n again because we need to store the mins and the maxes. So I'm basically copying the list several times. Excuse me. But that's the follow-up. Let's submit it and see if we pass. So the reason I wanted to submit it to Leetcode is because effectively there's hidden cases that I can't see and I can't download. So if this works, and it does, fantastic. That means my APL solution also works. What was I going to say? No, I think let's go back to the APL. This was very slick. I'm quite happy with the solution. So we do use Omega a few times in here. I'm sure the true APL aficionados would say this needs to be tacit, this yada yada yada. See if you could do a hook or something like that. I don't actually know if these are in GNU APL. That's what I'm using. They're probably in Dialog or in J or something like that. I'm not an APL expert. I will say that right now. On my other screen, I have the keyboard mappings just so I can actually type it in the text. But it is a very neat language and one that I definitely recommend people learn at some point, just so they can say they know an array language. It's really helpful if you're ever going to do any work also in NumPy and pandas, because they're based on actually the same philosophy. So these ideas of like doing a scan min and scan max in NumPy so I had to do a bit of a hack here to do it with lists, but in NumPy, these are, again, sort of built-in things. I think they're called cumulative min and cumulative max, or cumin and qmax. There's some very unfortunate ones like cum sum. But anyway, I think that'll do it for us today. Solve the problem in a very different way to usual. Do remember to like, comment, subscribe, all of that good stuff. And I will see you next time. Bye.